Hey everyone, this is Seth, and in this video, I'm going to talk about how you can use substitution to understand and simplify convoluted formulas. This is the third video in my series on prepping for your first statistics course in the social sciences. As I said before, arithmetic is really the core prerequisite you need: addition, subtraction, multiplication, division. What is actually tricky in statistics is just the ways that we combine these basic operations. It's sometimes confusing to think of how to break this down. And the answer to that is simply the order of operations, which I reviewed in the second video. Okay, this is it. And this gives us the way to solve convoluted formulas, but how do we actually understand them? I would argue what you need to do, what you want to do, is take anything like this that seems complicated at first and break it down into the parts. You want to be able to describe it in a sentence. The variance is the average squared deviation. So on average, how far away is a given score from the mean of that distribution in squared units? So this really only works if you use definitional formulas, which are sort of like versions that say what it's doing. Computational formulas are fine if you're doing it by hand or don't need to understand, or probably if you're programming it, it would just run faster. But for learning purposes, I would say stick to definitional formulas because we're going to be using computers to run these analyses. Okay, so in this video, I'm going to talk about how to convert this terrifying monstrosity into this relatively simple and straightforward representation. Now, I've made this extra convoluted on purpose. I almost made it even more convoluted than this, but I think this is enough. You're not going to see this particular representation of it, I don't think, but I started from an extra hard place just so you would know, no matter how ugly the formula looks, you can break it down. So fundamentally, what I'm going to illustrate to you in this video is a t-test, which you'll learn about in Stat 1. A t-test is a signal-to-noise ratio. So it's a fraction, and the numerator is the signal, and the denominator is the noise. Before diving into this, let's just identify each of the variables we see here. So when you see an M, capital M, that is a type of average. That is the sample mean, the arithmetic mean. So we've collected some sample data because we can't access the whole population. Whatever the full set of data that you're interested in, we have to take a sample of it. So maybe you survey a bunch of people. The sample mean is the mean for some variable in that sample that you took. Okay, then we also have mu, this Greek letter that looks like a U. That's actually more like a Greek M, actually. That's mu. This is the population mean. So the population is the full set of observations we would theoretically be interested in, but the sample is some subset of that we draw. If you want to know more about this, check out my video where I break down key terms and concepts, including samples and populations. I'll link to that in the description. So regardless, we've got the mean for a sample using capital M, and then we've got the mean for the population using mu. Okay, what else do we see here? We also see these s-squared values. That is the sample variance. I also explained that in other videos. Lastly, we have sample sizes. This is the number of observations in a particular group. So you might notice I've got some 1s and 2 subscripts happening. That's because a t-test is comparing two groups. So the mean of the first group minus the mean of the second group. And then we're also curious about things like, well, that's in our sample, but in the overall population, the thing we're trying to understand, the thing we really care about, what's the actual difference between that mean and the other group's mean? Then if we have two groups, we have two sample sizes. So in one is how big is the first group? In two is how big is the second group? How many observations are there? How many rows are there in your data set? Okay, and then we've got a variance for the first one. The variance is an index of how spread out the data are. So we have a level of spread for the first one and a level of spread for the second one. So those are just the different parts that are here. And it's honestly not really that important that you understand any of this right now. You just need to be able to see that we can take all this complexity and we can slice it down into something much simpler and more intuitive. So let's start using some substitution. The mean difference, so literally the difference, the first mean minus the second, the difference between those two means, that's our focal effect. That's the relationship that we're trying to understand. So simply subtract one from the other. Let's go ahead and do some substitution. This is actually a little atypical, but I sometimes like to use something like this. So delta is, it's kind of like a capital Greek D, but looks like a triangle, and it is a triangle. And when you say delta M or delta anything, that means change in this thing. So we could use delta M to say the mean difference, the change from mean 1 to mean 2. I'm just going to substitute that right into the formula. And this is kind of the key to substitution. We take an abbreviation or something smaller that stands for something bigger, and then we put the smaller thing into the formula because that allows us to start explaining it conceptually more easily. So this is what I mean by substitution. Replace something in the formula with something equivalent and hopefully simpler to understand. Maybe you look at this and you think, oh, we got the same thing happening over here. Why don't we just use delta mu here as well? And we can, that's totally fine. But we can take this one step further. So here's what's happening in the numerator. In a t-test numerator, we're comparing the observed effect, so this is the mean difference in our sample, to a hypothetical mean difference in the population. So this is what the true effect would be. And in a standard t-test, we're assuming that this is 0. That's just kind of the logic of null hypothesis significance testing. We typically think, how big is this effect compared to 0? So if we're testing whether the observed effect is, quote, significantly different from 0, we could just drop this term entirely. We could put a 0 there. And whenever you subtract 0 from something, you're left with what you start with. So this right term can just drop off entirely. Okay, so I've done a lot to simplify the numerator to a single term, just the mean difference. But it turns out we can simplify the denominator just as much. Okay, so let's go through that. And this is going to get a little bit in the weeds. It's okay if you don't grasp every single thing I'm saying. What's essential is just that you see how these substitutions are making the formula smaller and smaller, easier and easier to understand. Okay, so let's do it. First of all, I'm going to substitute df for n minus 1. So you're seeing these n minus 1s happening. That is what we call degrees of freedom, okay? So for right now, just see what happens. Okay, and so what just happened? I took each of these n minus 1 terms. So we have sample 1 minus 1, sample 2 minus 1, and I'm replacing those with degrees of freedom. So that becomes the first degree of freedom, that becomes second degrees of freedom. For now, just think of degrees of freedom as a function of the sample size. It's sort of like the effective sample size. It's the number of data points that actually help you evaluate your model, but don't worry about that. This will be a tricky thing you'll learn about in your first class. So this is some function of the sample size. Okay, now what's happening here? I know this looks scary. This is probably the scariest looking part of the formula, but this is called sample weighting, and it is actually not that complicated. I am going to go slightly deep on this just to show what's happening and where this comes from. So sample weighting is a way of combining multiple sets of data such that more weight is given to larger data sets than is given to smaller data sets. So for example, imagine we've got two groups. Let's say we've got 100 observations in the first group and 1 observation in the second. So a size of 100 and a size of 1. If we combine these two groups, The first group should get 100 times more weight than the second group because the first group is 100 times larger than the second group. This sort of principle will be very useful in statistics throughout any stats courses you take. The concept that having more observations gives us more trustworthy results. Okay, what if we had 25 observations in the first group and 50 in the second? In that case, the first group should get half as much weight because 25 is half of 50. Now, we can do this sample weighting for 2 or more groups for really any sort of descriptive statistic that I can think of. We could sample weight the mean, we can sample weight the variance, and so on. When we do this, it's called pooling them, okay? I'm going to start by showing you how to pool or sample weight the mean, and then we'll translate that to the sample weighted variance. So here's the formula for the sample weighted mean, or the pooled mean. This is the way I like to write it because it's pretty straightforward and simple. You take your first mean, and then you multiply it times the proportion of the total that it makes up. Okay, so for example, if the first sample size is 25 and the second is 50, this one is half as large as the second one. That is a 1-to-2 ratio. This one is 2 times as large. So imagine it's like if there are 3 pieces, 2 of the pieces are here, because that's twice as much. 1 of the pieces is here. Okay, take the first mean and then cut it down to 1/3 of what it currently is. Then take the second mean and cut it down to 2/3 of what it currently is. This is weighting. We're giving them the weight that they deserve based on how big the sample is. Let me show you a more common way of writing this formula, which should make it more obvious how I got to that 1/3 and 2/3. So the proportion for the first one is its sample size divided by the total sample size. So like 25 out of 25 plus 50, 25 plus 50 is 75. 25 out of 75 is 1/3. That's where that 1/3 came from. And then over here, 50 out of 75 is 2/3. So the proportion that the first one gets is 1/3 of the combined sample size. The proportion the second one gets is 2/3 of the combined sample size. So let's drop those parentheses and notice that we can rewrite this. If you're multiplying a mean times a sample size, and that mean times that sample size, we could just put that all on the numerator like this. Now, when you look at this, maybe you say, oh, look at that. We can combine those 2 denominators because they're the same thing. Okay, so this becomes this. Multiply each mean times its own sample size and then divide by the total sample size. Maybe it looks scary at first, but all that this says is sample weight the means. In other words, multiply them times the proportion that they make up out of the total, because that's how much weight they deserve. That's how much weight they're bringing to this party. And don't stress out if this doesn't make a whole lot of sense. This is something you can dive into later. The point is, here I've shown you how to sample weight the mean. For the sample weighted variance, the pooled variance, it's the exact same thing, except we're going to use degrees of freedom instead of the pure sample size. And you'll learn about why in Stat 1. Okay, so returning to our original formula, which is still looking kind of scary, we can say, wait a minute, this is just the sample weighted variance. That's that thing we're just looking at. So what this is doing is it's saying, let's pool the first variance and the second variance giving each one the weight that it deserves based on its size, the degrees of freedom. Okay, so that's happening over here and that's happening over here. So let's just simplify this by substituting in the term pooled variance for these 2 more complex expressions. Okay. That, to me, this is looking much better. This looks way less scary than it was before. But it gets even less scary because this particular expression has a name. This is the standard error of the mean difference. So we could represent that with standard error, SE, of the change in the means, delta m. I'm just going to substitute that right in. So the standard error of the mean difference is how large we would expect the observed mean difference to be purely due to randomness. So in other words, if the true effect, delta mu in the population, the actual true difference in the means in the population, if that is literally 0, this denominator is how big we would expect the numerator to be, just by chance. So if the true effect is 0, then we would expect this t statistic to be a number pretty close to 1, because we'd have some observed effect, which should be similar to the effect we'd expect due to chance. What this means is a t-test is a signal to noise ratio. The numerator is the signal and the denominator is the noise. How big is the effect that we observe, the mean difference? How big is that compared to what we would expect if this is just randomly generated data, or if the true effect is 0? So, and it's okay if that doesn't make perfect sense right now. The point is, we can take something that's just hideous and awful to look at, and using substitution, we can break it down into something much simpler. And now we even become able to speak about this. You could explain this to someone who's just learning about statistics. T-test says how big is the difference in the two means compared to how big it would be just due to chance. And then you can start to make some interpretations. Like if this is a value less than 1, we would say, oh, it's even, if this division results in a value like 0.5, we'd be like, oh, wow. So this effect is half as big as we would expect just due to chance. Maybe this really is just coming from random noise. Or if this value is 50, if you divide the change by the standard error and you get 50, you would say, wow. So our effect is 50 times larger than we would expect it to be just due to random chance. If the true effect is 0, that might make you think, maybe the true effect is not 0. Okay, that's kind of the backwards logic of significance testing. Not really going to go any deeper into that right now. Point is, we can start making some useful interpretations when we simplify with substitution. Okay, that is it. I think that does it for this introductory playlist. 3-video sequence on prepping for your first stats course. If you watch these 3 videos a few times, you're going to have the basic math fundamentals that you need. So I think you're good to go. If you have any questions, thoughts, comments, or concerns about anything that I talked about here, don't hesitate to reach out. That is it for today. Have fun. See ya.